And yeah, I'm just going to start talking about the class, which is lenses, interference, and diffraction. So more effects to do with light. All right. So first I'm going to talk about interference. So essentially what interference is what happens whenever two waves meet. So does anybody have any guesses what will happen if we have like these bottom things? So in this left, we have A and B that are going towards each other and they're kind of on the same side. And on the right, we have A and B that are going towards each other, but they're kind of upside down to each other. So does anybody have any guesses?
The first one where A and B are going to each other are going to cancel each other out, or like just stop. And the second one, they're going to keep on
going. Parts of that were right, but also parts of that were not right. But does anybody else have any other guesses?
The second one, the A will go on the bottom and the B will go on the top, and they will go separate ways.
I think that's right, but it's okay if you guys don't know any of this because I haven't like taught you guys, but like guesses are always really cool to have. So does anybody else have any other guesses they'd like to try? I don't know. It might be a bit unintuitive what would happen when we have two of these waves meet. So whenever wait, was somebody gonna say anything? I feel like I just heard somebody unmute, but okay. So whenever two waves meet, what's going to happen is just they're going to go right through each other, but at the point where they meet, right? So if we have A going into B, at the point where they meet, they're just going to go right through each other, but then because they're like going right through each other, at some point they're going to be right on top of each other, and whenever they're right on top of each other, they're going to form this big wave. But then after that, they're just going to separate back out. So based on this, does anybody have any guesses for what's going to happen on this right side?
They're going to cancel each other out.
Yeah, they're going to cancel each other out. And then afterwards, they're going to continue going through each other. So as you can see here, whenever the A and B, they're going to meet, right? And what happens when they meet is because you have a high part going with a low part, right? And then they're going to cancel each other out, right? It's like filling in, it's like a hill going into a valley, and they just like kind of cancel each other out. And then they continue moving forward to the other side, even after they meet. So essentially, whenever you have two waves that are going into each other, they're just going to pass straight through each other. But while they're passing through each other, they're going to add their amplitudes, right? I said the amplitude is the height of the wave, but when they're passing through each other, right, this A and B is twice as tall because that's what happens when you add the two amplitudes, and they're going to pass right through each other. But then with this A and this like negative B, right, they're going to like cancel each other out for a little bit, and then they're still going to pass right through each other. So this is what interference is. So it's what happens whenever we have two of these waves meet, right? And okay, and there's two types of interference that are like kind of shown in these pictures. One is called constructive and the other is destructive, which I'm going to go cover a bit more later. All right. So another way to visualize interference is if we drop two pebbles in a lake, right? Whenever we drop pebbles in a lake, they form kind of these ripples on the surface, right? There's going to be high parts and there's going to be low parts, right? There's going to be a lot of ups and downs and ups and downs and ups and downs, right? So as you can see here, like where they're meeting about, where the two ripples are meeting, we see like all of these little sections. Like we have these like little bumps and like little low points and high points, right? Because at like these points, we're going to see lots of high points here that are mixing up with other high points that might be canceling out with low points, or low points that might be getting even lower because they match up with the low points of the other wave, or it might have other places where these low points are canceling out with the high points, right? So two pebbles in a lake can be a good example of interference because they can show like all of the repeated ups and downs and how they're going to cancel, and there's going to be many points where you're going to be adding waves together, and there's many points where they're going to be subtracting from each other, right? So does anybody have any questions about those first two slides?
What happens if like a middle wave like hits like where's like in the very middle hits like a high wave? Like does it just go high?
Yeah, kind of just goes high. So you're trying to like, if it's like at the center point and it meets up with something that's like at this like peak, right?
Yeah.
Yeah, it's just gonna like, they're just gonna add, right? So we have like 0 plus like something that's like pretty high, right? Which means it's probably gonna end up the same size as this, right? But if like, I don't know, something in between, right? So if we have like this high point, but we have something that's like somewhat low, what we're going to get is something that's still going to be high up, right? But it's going to be like somewhat lower than what it is because this high cancels out with this low, right? So it's just like adding and subtracting, right? Does that make sense? Okay. So I said before that there are two types of interference, and one of those types is constructive interference. Essentially, it's whenever things nicely line up, right? On the first slide, I had like two like waves going towards each other, right? Let's see here, somebody said something in the chat. So I said in the first slide, they had two waves that were like going up, that were going into each other, right? You remember that first slide, we had like this wave that was going into this wave, and we got a bigger wave, right? So this is constructive interference. And essentially, whenever waves are going to be adding together because they're going the same wave, they're going the same way. In sound terms, this would be like whenever we have two waves, right? Whenever we have two speakers, we have one speaker, it's like kind of like not too loud, but then we add another speaker and suddenly it's louder, right? Because we're going to might see constructive interference of the waves, right? And if we have constructive interference, then because of constructive interference, the amplitudes are going to add and the volume is going to increase, right? And then, does anybody have any ideas what would happen if we like had two longitudinal waves or like constructively interfering? Anybody like remembers longitudinal waves?
They add together.
They will add together, but like that's kind of the intuition for it. So if you remember longitudinal waves, there were like places where there are a lot of particles and places where there are less, right? It's kind of like
The
what happens.
particles will add.
Yeah, kind of like that. Because if we have like two places where there's like two places of high densities of particles, right? That density of particles is going to increase even more, right? Which means that in effect, we've increased the amplitude of the wave, right? So this works, constructive interference even works with longitudinal waves. And it kind of makes sense because sound is a longitudinal wave and we still hear like louder sounds because of constructive interference, right? So we can see constructive interference with sound, and it's essentially just where waves add together. Whenever you have, for two waves to constructively interfere, as you can see here, there's like kind of this thing that says in phase and out of phase. So essentially, whenever for two waves to like line up properly, right, they have to be in like the same positions, right? Otherwise, you're going to get places where we're going to see cancellations, right? So to get constructive interference, the waves have to line up, right? We have to have the high points line up with the other high points, we can get super high points, and the low points line up with other low points, so we can get super low points, right? So this is constructive interference.
Is the next one just destructive interference? Oh, yeah.
Yeah, it's destructive interference. So as you can see, I'm using the same picture because at the top it has constructive interference and the bottom is like destructive interference, right? So
yeah,
if you remember on the first slide, we also had another thing that was like one wave that was going up and the other wave that was going down. And when they ran into each other, right, it became nothing, right? And then after they passed through each other, they like still were there, right? Essentially, it's when waves that are like opposite to each other, right? So we see an up where there's also a down, and they're going to quote unquote add, right? But it's more like we're subtracting, right? Because we're adding a negative number, right? So in sound terms, if we have like a high point and we cancel it out with like a wave that's like perfectly like it, except like the opposite way, the amplitude will get to zero, will drop to zero, right? And it's going to be softer, right? This is actually how sound canceling headphones work. They create the opposite wave that just so happens to correspond with, they create the opposite wave that corresponds to whatever wave's coming in, and it makes all of the waves cancel out. All right, so does anybody have any ideas what would happen to longitudinal waves with destructive interference?
It would just remain zero, like go to zero, like a straight line, or cancel.
They would add.
I mean, they would like add, but then like they're also like kind of opposites to each other, right? So they would like go to zero, but like in the sense of longitudinal waves, which are like based on dense particle density, right? Like sound, right? What would happen is that since the high points are like lining up with the other high points, and the low points are lining up with the other low points, what's going to happen is that like everything is just going to return to normal. Like the high pressure areas are going to match up with the low pressure areas of another wave. And then what's going to happen is that that pressure is going to like return to normal, right? So all the pressure is entirely going to balance out. And you can kind of see like a visualization of this on the picture, right? Of constructive interference, if you think of all the darkened parts as the peaks of the waves, right? So all of those darkened parts, like here, these are the peaks of the waves, right? Whenever they line up with each other, we get even darker peaks, right? But whenever they like kind of like interweave with each other, so the light stuff lines up with the dark stuff of the other wave, light with dark, what's going to happen is we're going to see destructive interference. It's kind of like a constant cancellation, right? So we're not going to hear anything from this point because all of the waves are canceling out, right? All right. So does anybody have any questions about constructive interference and destructive interference? Probably clear all of the annotations. Okay. Now we can also have this occur on a larger scale, right? So previously we were only dealing with like these singular wave things, right? They're going into each other, like we have like one wave that's going up and like another wave, right? But we can also have waves that occur like in 2D space, right? And they propagate out, right? So we have a source coming from here and a source coming from here, right?
Wait, isn't this like the Pebble thing?
Yeah, this is like exactly like the Pebble thing. Yeah, that's exactly right. We're gonna see. So you can think of this as like an analog to like the Pebble as like an analog to think about how this might work. Or also, you can also think of this as a way to think about what would happen if you drop two pebbles into the ocean, right? And as in the dot, with the like hard lines represent the high points, and dotted lines represent the low points, right? And this figure looks a little bit busy, but essentially, as you can see, if we like look at just one of these points, right, we're gonna see like this is a full line, and this is a dotted line, and this is a full line, and this is a dotted line, right? We see these alternating full lines and dotted lines, right? Because in a way, we're gonna have peak, trough, peak, trough, peak, trough, peak, trough, right? And we also see something similar happening to the other one, right? A peak, and then we have like a bottom part, then we have a peak, we have a bottom part, right? So what's going to happen because of interference is that wherever we have two of these waves have their peaks, right? So that would be maybe, I don't know, this point, we see these two waves have their peaks, or maybe this point where they have their peaks, and this point where two waves have their peaks, right? What we're going to see here is constructive interference, right? Because we're adding in the two high amplitudes, right? So two high amplitudes are going to create an even bigger amplitude, right? And over here, these are exactly where we have two low parts, right? So we have two low parts, and that's going to create an even bigger low because of interference, right? So along this line, like this line labeled C, we're going to see very high peaks, and we're going to see very low bottoms, high peaks, and low bottoms, right? So this is where we have like constructive interference is at its maximum, right? And meanwhile, on this line, we see that we have coinciding, we have this section of low, or this section of high, and then this dotted line section of low, right? So this is going to cancel out here, right? This is also going to cancel out here because we have a low with a high, and again here because we have a low and a high, right? So all along this line, we're going to see the wave is going to perfectly cancel out, right? So we have one of these high sections that are mapping to like one of these low sections, right? So in this entire like section, in this image, we're going to have places where we're going to have lots of constructive interference, right? So the wave is going to get stronger. We're also going to have places where there's like destructive interference, or perfect destructive interference, right? Where the wave is going to get weaker, right? So does anybody have any idea what would happen if we like walked across this room?
There would be a bunch of waves.
There would be a bunch of waves, but like I was thinking of more about like what you would hear if you're like walking across this room.
Like constant chitter, and like it's not too loud or too soft.
I don't think it would be constant, right?
It's like a bunch of ups and downs.
Yeah, right. As you walk across this room, you're going to hear places where they're going to like perfectly cancel out, and you're not going to hear very much, right? And when you get to other places, you're going to hear it very loudly because they're going to like perfectly line up with each other, right? And okay, right? So as you're walking across this room, you might hear sections where it's like louder. You're going to hear sections where it's softer, and you're also going to hear like sections where it's like not as loud or like not as soft. So does anybody have any questions about like this thing? Oh, you might also see this like on a stream where you drop like two pebbles in, right? If you like notice the pebbles like really clearly, you're going to see like these perfectly nice lines, right? That you're not going to see very much movement in whenever you drop in those two pebbles, which is like kind of crazy to me, but. And you're also going to see like these lines where there's like really a lot of movement happening, right? That's kind of what this tells us. So does anybody have any questions? All right, and move on to the next slide. That's not the next slide, that's the previous slide. Whoa. So I mentioned this briefly before, but in phase and out of phase, right, with the image. And in phase just means like the waves are nicely lining up. I showed this before. If we have like a peak that's lining up with a peak and a like trough, or a bottom that's lining up with a bottom, right? They're going to perfectly constructively interfere with each other, right? So that means they're going to add to each other, right? They're going to go from like two medium-sized waves to one big wave, right? And whenever they're out of phase is whenever they are perfect destructive interference, right? So we have these high sections with the low sections, right? And they cancel out. So whenever they're out of phase, in phase means that they look the same, right? So in phase, these two waves are in phase. But if you're like perfectly out of phase, right? That means that the two waves are opposite to each other. But there's also somewhere in between, right? So here you see some like 90 degrees out of phase. You like don't really have to know like what these degree measures like mean for like in phase and out of phase, I guess. But as you can see here, these like don't perfectly like aren't opposites of each other, but they aren't like perfectly adding up with each other, right? So we have this wave, and they're adding to create the third wave, right? So here we have a high point, but it's like not lined up with another high point or a low point. It's like kind of like in the middle point, right? So what we're going to get is like that same high point, right? But then as we go down further and further, here we're going to have like destructive interference, and they're like perfectly going to cancel out with each other to form zero here, right? But then as we move to the right, here we're going to have like these waves are going to be perfectly adding up to each other to form this sort of peak whenever we have these two waves that are added up, right? So this is like sort of an example of constructive interference. And here we have destructive interference because the waves are canceling out, right? And like here we have more destructive interference, right? So whenever waves are like not perfectly in phase or out of phase, we're gonna have points where they're like gonna mash up and like they're gonna go against each other, but they're also gonna have points where they're gonna like work together and form these like extra high peaks, right? Anybody have any questions about like this phase stuff? Okay, so we can also have, we've mostly just been dealing with whenever we have for interference, we've mostly just been dealing with interference whenever the two waves have the same frequency, right? Because like we were saying that these peaks are going to perfectly line up with another peak, right? Like these bottoms are going to perfectly line up with the bottom, right? But this can only happen if these waves are like the same length, right? But they don't necessarily have to be the same length, right? Like what if we had like a super like short laying? What if we had a super short one, super short, what is it? Super short wave, and we had a super long wave, right? Then the peaks might not like add up with the peaks, right? We're gonna have like, we're gonna see constructive interference here, but we might see destructive interference here. We see destructive interference here, right? Since they're not gonna be like perfectly adding up with each other, if they have different frequencies, they're not like going to correspond with each other, right? We're not going to necessarily have high points of high points at one point is not going to necessarily imply high points of high points at a later time, right? So if we have like a smaller wave, we have like a high point that might line up with like another wave's high point, right? But because this taller wave, this first wave has like a shorter wavelength, right? This bottom here doesn't necessarily line up with like this bottom here. That would imply perfect constructive interference, right? So once again, like with the like kind of middling between in phase and out of phase, we're also going to see some points where we're going to have constructive interference. We're also going to see other places we have destructive interference. Now what happens when we add these two waves together, what you're going to get, oh boy, I just maximized chat. What you're going to get is something like this image on the right. So as you can see here, the waves have very similar frequencies, but they're very slightly off. So at some points, like here, we're going to see nearly perfectly constructive interference, right? We're going to have these low points that are lining up with these low points, these high points that are lining up with these high points. And because these waves have such similar frequencies, that doesn't drift very much like within this little tiny area, right? But as we slowly go to the right, these waves are going to get more and more out of sync. And eventually they're going to become so out of sync that the high point of one matches up to the low point in the other, right? And we're going to have perfect destructive interference here, like nearly perfect destructive interference here, right? So whenever waves have two different frequencies, we're going to get these points where we have high frequency, high amplitudes, and we get these points where we have low amplitudes, right? So it's going to constructively interfere where it has high amplitudes, right? And it's going to destructively interfere where it has low, destructively interfere at these low points, right? And this actually has a lot to do with music. So whenever you have like two instruments that are like tuning against each other, right? They might be like playing the same note. If the instruments aren't perfectly in tune, what you're going to hear is you're going to hear the note. It's going to get louder, right? It's going to get louder, and it's going to get softer, and it's going to get louder, and it's going to get softer, right? Because of this sort of interference thing we have here, right? It's going to get louder at these points and softer at these points because they aren't like perfectly lining up with each other, which means that you can tell if two instruments are in tune, if you play like the same notes with each other, and if you can hear like, whoa, whoa, that means that the instruments are not going to be in tune with each other, perfectly in tune with each other, because we're hearing this increase in frequency and decrease in frequency that we can only get whenever they have, not frequency, increase in volume and decrease in volume that we can only get whenever the waves have two different frequencies, right? I find that kind of interesting. And whenever you have like two waves that are like perfectly in tune, they're just gonna like perfectly line up with each other, and they're gonna like add up with each other, right? So does anybody have any questions about like what happens with interference when we have waves of two different frequencies? Oh, I forgot to mention some like mathematics of this. Oh no, mathematics. This is not hard mathematics, I promise. So if like one of the wave has a frequency of like f1 and the other wave has a frequency of f2, then the frequency of like going louder and softer, right? Because there's going to frequency, you can see like this kind of follows an overall pattern, right? If you draw a wave, it's kind of like lines up with each other, right? There's actually a formula to calculate how regularly this like wave goes up and down. So it's f1 minus f2, and you have two, and it's the positive of this, right? So if you have like 340 and 343, right? Handwriting is not the best, but it would be 340 minus 343, or 3, or negative 3, right? But then this, like, we're looking for the positive part of that. So we're ignore the negative, it's just 3. And that's how the frequency of the wave going up and down and up and down. Oh boy, math. All right, are there any questions about this? Okay, I'm going to move on to the next slide then. All right, so now we have some review questions. I just realized that I'm like halfway through my time and I haven't gotten through my first topic, even though there are 3 topics, which sets me on a good pace to do exactly 2 out of the 3. Oh boy. All right, so does anybody know what interference is? Hope you guys know what interference is.
When two waves interact.
Yeah, it's when 2 waves interact and they might like add or subtract, right? Right, so they might add, they form a bigger wave, right? Which leads us into the next question. What is the difference between constructive interference and destructive interference?
Constructive interference is adding, and destructive interference is canceling out / subtracting.
Yeah, right. So, I mean, they're both technically adding, right? Because destructive interference is just adding a negative number, right? Adding a negative number is the same thing as subtracting, right? So we have like this up and down, right? And they're like going to add up with each other to form this, right? And that's destructive interference. And constructive interference is what they have up here. We like add 2 waves and they form an even bigger wave, right? So that's like the difference between constructive interference and destructive interference. Okay. Next, what does it mean for 2 waves to be 180 degrees out of phase? I didn't exactly mention degree measures. It's fine if you guys don't get this, but props to you if you can understand what this degree measure thing for phases is. Okay, so the degree measure of like how many degrees out of phase something is kind of like, in a circle we have 360 degrees, right? So in a wave you can kind of consider.
Oh, they're opposite. They're like opposite. They're like exactly destructive.
Yeah, it's exactly destructive, right? So for 2 waves to be 180 degrees out of phase, they're like kind of opposite of each other. So what I didn't explain phase, like degrees in phase and out of phase exactly clearly, but if you imagine, right, that this is like 360 degrees, right? Then being 180 degrees out of phase means that you're starting the wave 180 degrees late, right? So we're starting the wave here, and we might have 180 degrees here, right? Because it's exactly half of 360, right? I know, it's like a little bit confusing, but. So being 180 degrees out of phase means that we're going to perfectly cancel out. And if we're like completely in phase, right, then we're going to be 0 degrees out of phase, or 0 degrees out of phase. It's not even going to be out of phase because we're in phase, right? So it's going to when the 2 waves line up. And finally, what happens whenever waves of different frequencies interfere with each other?
big, small, big, small, big, small.
Yeah, overall, we're going to see like these points, we're going to see like really small sections, and we're going to see it grow larger and larger, and it's going to have bigger sections, and it's going to grow smaller and smaller and smaller, right? This is what was happening in the previous slide whenever you have two like notes of like different frequencies, right? All right, does anybody have any questions about interference overall? Okay. So it leads nicely into our next topic, but like it might not be apparent how it leads nicely. Diffraction. So diffraction, as I said, like I said this on like the first week, right? And I said it about radio waves, right? Radio waves have the ability to bend around stuff really nicely. So essentially diffraction is where waves bend around objects, right? In this left image here, we can see like the wave or the ocean waves, they're like coming in. I said like these ocean waves are nice analogs for actual waves, like, right? We use the ocean waves like for ripples whenever you drop two pebbles in a pond to show constructive and destructive interference. But we can also see diffraction in these waves. And it's whenever waves that bend around objects, right? So whenever we have the ocean going through a small section of land here, right? Instead of like going in one straight line, the water is going to fan out, right? Or it's going to bend around these obstructions, right? This is partly why I can hear sound around the doorway, right? So as you can see, we have Jack and Jill over here. Even though they can't see each other, they can hear each other, right? That's because when the sound goes through the doorway, it's actually going to bend around the doorway, right? This is actually like not entirely like the only reason that we can hear sounds around a doorway. You can also hear sounds around the doorway because sounds reflect off a lot of different objects, including the walls, right? So the sound is going to reflect off the wall. But diffraction is part of the reason that we can hear around doorways, right? Okay. Does that make sense? Any questions about diffraction right now? Okay, so with diffraction is just when waves bend around objects. Right? So here, earlier we had like waves, they're going through a slit, right? Because they're going through a small section, right? Here waves have a little bit of area to go through. And on the right side, we also see that these waves also have a little bit of only like a little tiny slit to go through, right? Here is the doorway. On the left side is like this, this part where the water can go through the two sections of land, right? But they can also bend around objects, right? This is what makes radio waves useful, right? Radio waves can easily bend around like giant buildings, right? These, if you imagine like this is a building and this is like a radio wave, right? The waves can easily bend around these large buildings because of diffraction. It's like why we can hear sound around the post, right? Because even though this post is like not like a slit, right? The wave can still be allowed to bend around it. So this is like non-slit diffraction, I guess. There's also a major difference between when the slit is large and when the slit is small. Right, so whenever the slit is large, you're not going to be able to, the diffraction is not going to happen very much. So whenever, as you can see in like this first image, right, we have a whole bunch of sections where we have like these waves that are going straight out, right? This is like what we'd expect because they're like going straight through, right? And on these rest of these sides, right, we see these like less pronounced parts where the wave is bending around this, the wave is bending around the wall, right? However, whenever we get into like a smaller slit, we're going to be able to more easily see the parts where the wave is bending around the wall, right? So whenever we have a barrier, the closer together two sides of the barrier are to each other, the more pronounced or like the more obvious the effects of diffraction are, right? So whenever the wave, this slit is large, we're not going to see very much diffraction, right? And it's not going to bend very much around the wall. But whenever the slit is like really thin, right, we're going to see that this wave is going to bend around the wall a lot. The smaller the slits, the more diffraction there is in general. Does anybody have any questions about the previous two slides? Okay, so we can also here see diffraction causing and diffraction interference interacting with each other. So like earlier we had like this image where we have 2 point sources. Does anybody have any ideas of how we can create point sources with diffraction? If you like think about the previous slide, right? This image here on the far right, right? That's already kind of close to what is it? Circular perfect point sources, right? Or perfectly like propagating circularly outward, so coming from a point source, right? So we can actually get point sources if we have just like this little tiny slit here, right? The tinier the slit, the more pronounced like it's going to bend around, right? That means that we're going to get very pronounced parts. We're going to get very pronounced like circular waves, right? And it's exactly what a point source looks like, right? Because a point source just kind of looks like circles coming from one point, right? So this looks exactly like a point source, right? So this diffraction here, which is causing the light to bend around, is sort of creating this sort of, it's creating like what's necessary to create like a point source. So I believe on the next slide, right? So we have one wave, and because it's like going through this wall with like very small holes, from those very small holes, we're going to have essentially what are point sources, right? So that means that we're going to see parts we're going to have constructive interference, right? If you remember from a little bit a while ago, we saw like these lines. I don't know, probably these lines are like really close together. So I'm like, these lines right here, you have like constructive interference and destructive interference, right? And what's going to happen is because we're going to have points where it's going to like vary a lot, right? These are high amplitude waves and like waves where it's not going to vary very much. We're going to see bright spots on the back wall. We're going to see bright spots where we have constructive interference, and we're going to see dark spots where we have destructive interference, right? So this is diffraction and interference working together to create like these like dark and light bands. These bands, yeah. Bright and dark bands. Okay. Does anybody have any questions? Accidentally hit. Okay, now we're back. I accidentally hit one of my tabs at the top. Oops. All right. Oh my God, I'm trying to open chat again. Okay. All right, and we can also get these sort of patterns here with only one slit, because I said before that you needed to have like 2 point sources to have like, what is it? You need to have 2 point sources to have these sort of patterns here, right? Because we need 2 sources to interfere with each other. We can actually see these patterns with only one slit, right? So we have this wave that's going through one slit, right? But we're still going to see these light and dark bright bands, and we're going to see these dark bands, right? What's actually happening here is that each of these like corners, since the light is diffracting around each of these corners is actually going to create its own it's going to create its like own kind of, what is it? Point source kind of thing, right? So if the blue represents the high parts of the wave and the red represents the low parts of the wave, right? Because we're going to see these waves coming from both of these corners, right? We're going to get a similar effect as if we had two holes, but now we only have one hole, right? So we can have the light. Also, we can also see these patterns back here, even with just one slit, which is kind of crazy, I think. What you're going to see on the back wall, if we have one slit and like a light source, is we're going to see like one big centered bright band, right? Because most of this light is just going to like go straight through, right? But on these sides, we're going to have these bright parts where we're going to have like constructive interference, like parts where the wave is going to like just so happen to line up from this part and this part, and they're going to destructively interfere. And up here, we're going to have waves parts that are like perfectly lining up to create these bright spots up here, right? But overall, we're going to see most of the light travel straight through. All right, is there any questions about seeing diffraction from like a single slit? Okay. Now, there's also a lot of other examples, there are other places where you can see diffraction, right? We can see it like in the stork way, right? We can see that this light is like creating, it said before that you can get diffraction from like a single slit, right? So this doorway here is creating like between the store and this wall, there's going to be like a tiny opening, right? And this tiny opening is creating like these sort of light bands and these darker bands, and we're going to see light bands and darker bands, right? So this doorway is an example of lighter, brighter, and darker spots, right? And we can also see these brighter and darker spots and these diffraction in this image over here, right? We're shining a laser through this grating, right? This the diffraction grating. So a diffraction grating is just it's like a just a piece of plastic or whatever that just has a whole bunch of like little slits in them, right? Remember like a polarizer from like the previous thing, and like these are exactly the same thing. So it's essentially when we have like just like this object here that's just like a whole bunch of vertical lines, and what this creates is a whole bunch of slits, right? As we said before, diffraction, you can see diffraction coming from slits, right? So even in this like image here, we can see diffraction, right? We see these light spots, we see these dark spots, light spots, dark spots, right? With this laser, because it's like splitting off, right? Okay. And I said before that like the length of the slits impacts how much diffraction occurs, but also the wavelength will also impact how much diffraction occurs. So you may remember from the first week's class, when we were like going through the electromagnetic spectrum, I said that red is like long wavelengths, right? And blue has shorter wavelengths, right? So this means that if we have a corner, red light will bend around that corner more than blue light will. Now, normally you don't see a very big difference, right? Because we're not going to diffract light very much. You're going to need a very small slit to cause diffraction, right? But overall, red light is going to bend more, right? So here on the right, you might see an example of why, the intuition for why, like, longer wavelengths will bend more, right? Because the longer wavelengths you have, the more that you can like use that wavelength to bend around big obstructions, right? While the smaller wavelengths, they don't like have very much space to like bend around with, right? Because with these like longer wavelengths, you have a lot of section where you're like in this down portion that you can pass through the gate at, right? All right. Are there any questions about like longer wavelengths and like diffraction? So overall, just longer wavelengths. So that means like red light and like red light is more likely to bend or diffract than like shorter wavelengths, like blue light. Right, I'm going to go to the next slide. There are actually many uses for diffraction, and one of them is for spectral lines. I said before on the previous slide that different wavelengths bend more than others, right? And you actually see this if we have a diffraction grating. And with a diffraction grating, this allows us to separate out white light into all of its component colors, right? Normally, if you're like see white light, like all of the white lights, right? We'd see this entire spectrum of colors, right? But if we're getting it from a certain source, we might only see certain wavelengths of light, right? We might only see this yellow, or we might only see this orange, or a combination of this orange and yellow and this blue, right? So actually, whenever like each of these elements burns in like stars, what's going to happen is based on their wavelength, based on like what's burning, they're actually going to produce all of these different separate colors, right? When it comes to Earth, it might all seem like, oh, it's all one color because they're all mixed up, right? But essentially, what diffraction ratings allow you to do is allows you to separate out those lights, right? Because they're all going to bend in a different way, right? So like in a prism, we see like different wavelengths of light bending. So you can imagine this diffraction grating is just like a super duper prism, right? It's really good at separating out different wavelengths of light, so much so that like you can see it like out each of these bands completely separately, right? Which means that these diffraction gratings can actually allow us to see like what's burning off in like distant galaxies, right? So you might hear, oh, we know that this planet, yada, yada, yada planet is composed of this element, this element, this element, and this element, right? And the way they actually figure it out is through spectral lines. It's through analyzing the light that is coming from whatever is like really, really far away, right? And seeing what colors there are in there, right? Because if there's like sodium someplace, we're only going to see this like blue, we're going to see blue, we're going to see this like whatever color this is, we're going to see these lines, right? But if it's like hydrogen that's like over there, then we can see these lines instead. Before we use the diffraction grating, it's all going to seem the same, right? Because it's all going to seem like white light, right? Because they're all going to be combined together. But after they pass through this diffraction grating, we can see exactly what wavelengths are coming from all of these sources, right? Which means that with diffraction, we can see the colors in far-off galaxies. We can see the colors in far-off galaxies, which will allow us to see all of the elements that are in far-off galaxies. All right. Does anybody have any questions about like how this relates to like being able to tell the compositions of like far-off stars and galaxies? Okay, I'm going to move on to the next slide, which is just going to be review. All right, firstly, what is diffraction? Hopefully you guys know what diffraction is, since I've been talking about it for the past 20 or so minutes.
Like the weird splitty thingy or whatever.
What? Could you repeat that?
The splitty thingy. Like where it splits.
That's part of diffraction. It can like split each of the different colors of light, right? Like, what exactly is diffraction, right? Earlier we had like this barrier here. Yeah, it's like waves going around walls and like bending around it, right? I said that radio waves are very good at bending around walls, right? And that's because if you like combine that with this earlier thing, I'm not going to cover lenses, Let me combine it with this earlier thing. I said like wavelength, the longer wavelengths diffract more. And if you remember from like the first week, I said that radio waves have the longest wavelength, right? So because they have the longest wavelength, right? Because they have the longest wavelength, they diffract the most, and it's what makes radio waves so good at bending around like towers and stuff and buildings and whatnot. Okay, so next question is, anybody know where we see diffraction? A lot of different examples that you can use here. Oh boy, I closed chat for some reason. That was a smart move. I wouldn't say that we would see diffraction in like water. Like you'd have to be a little bit more.
Real life. You can hear sound around the corner.
Yeah, hearing the sound around the corner is like a perfect example of like, wow, we know that diffraction exists because we know that we can hear sounds going around corners, right? So we might see like diffraction, like with the water thing, we might see diffraction if we have like a wave pool here and we're going through like this tiny slit and we can see the like waves like bending around like the circular fashion outside of the slit because the waves are bending around the barrier. Oh, there's like this really cool lab that you can do in physics class. You should do physics. Physics is fun. Where like is where like they turn off the lights and they have like these little wave pools and they have like this like machine that can like create waves in the water, right? And they give you a whole bunch of things that you can put into the water, and you have like the only thing that you can see, or the only thing that way that you can see is that there's like a light that like goes right over the water pool, and at the bottom you can see like where there's lots of water and where there's not very much water, right? Because where there is a lot of water, it's going to cast a shadow, right? So you can see like how waves are like interacting based on this like water example, right? It's like really cool. Recommend. Physics is fun. Okay. So next question is, what role does the length of the slit play, right? So have like bigger slits, or we can have smaller slits, right? Smaller holes, bigger holes. Yeah, how round the wave is like kind of a good way to visualize it, right? Because if you like think about it, like whenever the waves are coming out like these bigger holes, they're not going to be like very round, right? They're going to have like this massive flat section, right? However, whenever we have a smaller slit, we're going to see like these more circular shaped things, right? So how round the wave is kind of like a good way to visualize diffraction, the differences between diffraction when we have a small slit and a large slit, right? And somebody else said, directed message me, said that, yeah, in general, if you have a smaller slit, you're going to have more diffraction. And if you have larger slits, you're going to have less diffraction. Okay. Now I've talked about the length of the slit. What about wavelength? May have covered this a little bit with radio waves, but the more fat the wave is, the more it can pass through. Yes, I guess it's a interesting way of stating it, but it like definitely is like a way to visualize this, right? So the bigger the wave is, or the longer the wavelength is, right, the more easily you can bend around the sort of these obstructions, right? If we have a smaller wavelength, it's not going to be as easily to like bend around, right? So the higher the wavelength, the more the wave is going to bend. And we can see this in like the previous example, right? Like spectral lines. Finally, how can we use the wavelength, the role that wavelength plays to see interference, right? Remember at the previous slide, intent. So we know that interference exists because longer wavelengths are going to bend more, right? Because if we have light that's shining through, right, we know that interference is happening if we have like red light all the way over here and we have blue light near the center, right? Because we know that this can only happen because the wavelength is causing the red light to bend all the way over here and the blue light to bend a lot less. All right, I didn't like cover lenses at all, but it's already 8:01 and this is kind of a good stopping point. So I'm going to stop the class here. So does anybody have any final questions about interference